Japan just detected X-rays coming from 3I Atlas. This has never happened with any interstellar object before. Never with Oumuamua, never with Borisov, never with any comet, asteroid or visitor from beyond our solar system in the history of astronomical observation. And while that discovery was being processed, while scientists were trying to understand what it means, something else was happening. Space agencies across the globe quietly began running defense drills, coordinated exercises, synchronized responses, planetary defense systems that normally sit dormant suddenly activating in unison across multiple continents. The timing is impossible to ignore. We are 8 days out from 3I Atlas's closest approach to Earth. 8 days until this object, travelling at speeds that defy casual comprehension, passes within our cosmic neighbourhood at a distance that, while safe by astronomical standards, brings it closer than any confirmed interstellar visitor has ever come. And in those final days before closest approach, governments are acting like something matters, like something requires preparation, like there's a scenario they need to be ready for even if they won't say publicly what that scenario is. I'm here to report the information without bias, without telling you what to think, without claiming I have answers that no one has. What I can give you are facts, documented observations, official announcements from space agencies, statements from researchers who are watching this object more closely than anything they've studied before. And the pattern that emerges from those facts, well, you can decide what it means. You can draw your own conclusions. But the pattern is there. It's visible, it's documented, and it demands attention. Let's start with what we know for certain. The European Space Agency, ESA, launched a 3-day simulation exercise that activated their full planetary defense setup. This wasn't a routine drill. This wasn't something scheduled months in advance and executed according to a predetermined script. This was comprehensive. This brought together rapid response teams from multiple countries, mission control hubs coordinating in real time, ground-based monitoring networks that track objects in space suddenly working at full capacity, tracking trajectories, calculating impact probabilities, testing communication protocols between agencies that don't normally coordinate this intensively. For a system usually kept on standby, for infrastructure designed to sit dormant until an actual threat emerges, this was unusually active. ESA's planetary defense systems exist specifically for scenarios where Earth faces potential impact from an asteroid or comet. They're not designed for routine observation, they're designed for emergencies. And yet, here they are, fully activated, running simulations that test every component of the response chain, from initial detection through public notification, from trajectory refinement through potential deflection mission planning. Japan followed with its own drill. JAXA, the Japanese Space Agency, conducted an impact scenario exercise that went beyond just space agency personnel. They involved civilian authorities, local government disaster response teams, defense units typically focused on terrestrial threats, private satellite operators whose assets would be crucial for tracking and communication during an actual emergency. This was whole-of-government engagement, the kind of exercise you run when you want to make sure every piece of the response machinery works correctly. When failure isn't acceptable, when the scenario you're preparing for matters enough to justify disrupting normal operations and pulling resources from other priorities. And then the United States Space Force made a decision that should raise eyebrows. They moved forward a major tracking rehearsal that was originally scheduled for late 2026. They didn't just slightly adjust the timeline, they pushed it up over a year. More than 12 months of advancement. That's not a minor scheduling change. That's a deliberate acceleration, a decision that required justification through multiple levels of command, that required resources to be reallocated, personnel to be redirected, systems to be prepared ahead of schedule. You don't make that kind of decision lightly. You make it because something has changed, because the timeline matters, because waiting until 2026 is no longer acceptable. Australia, South Korea, Brazil, nations spread across multiple continents, different time zones, different political systems, different priorities, all joined the exercise program, all activated their monitoring systems, all began sharing data through newly established protocols, using communication channels that apparently existed but weren't being actively utilized until now. The coordination is remarkable. The synchronization suggests planning, preparation, agreed-upon triggers that caused multiple nations to act simultaneously rather than independently. And then there's the International Asteroid Warning Network, IAWN, the organization responsible for coordinating global response to near-Earth object threats. They updated their protocols. Specifically, they now allow temporary use of classified monitoring data for objects labeled as non-standard hyperbolic bodies. That phrase, non-standard hyperbolic bodies, is careful language. It's specific. A hyperbolic trajectory means an object isn't bound to the Sun, that it's passing through rather than orbiting. But non-standard implies something else. It implies deviation from expected behavior, characteristics that don't match the standard profile, observations that require special handling. And the permission to use classified monitoring data, that's extraordinary. Classified data exists for national security reasons. Sharing it, even temporarily, even with international scientific partners, requires high-level authorization. It means someone decided that whatever threat or uncertainty 3I Atlas represents, it's significant enough to override normal security protocols. The information advantage of keeping capabilities secret is less important than the coordination advantage of sharing data to build a complete picture of what's happening. Now, to be absolutely clear, and I want to emphasize this because it matters, there is no official suggestion that 3I Atlas is on a collision course with Earth. The trajectory calculations are public. Multiple independent teams have verified the orbit. The object will pass at a safe distance. There's no impact scenario, no moment when this visitor threatens to collide with our planet. Officials across every space agency involved in these exercises have maintained that there is no immediate threat, that the drills are precautionary, that they're using 3I Atlas as an opportunity to test systems that need testing anyway. But context matters. The scale of these exercises, the synchronization, the acceleration of timelines, the sharing of classified data, the activation of systems designed for emergency response, all of this suggests something beyond routine testing. Governments are treating this anomaly seriously. They're using 3I Atlas as what they call an unexpected stress test for planetary monitoring systems. And maybe that's all this is. Maybe they saw an opportunity and took it. An interstellar object passing close enough to track in detail, unusual enough to justify comprehensive response preparation, creating a scenario that tests capabilities in ways planned exercises never quite achieve. Or maybe there's more to it. Maybe the stress test language is cover for genuine concern, for uncertainties that can't be publicly acknowledged, for scenarios that risk causing panic if discussed openly. We can't know from outside the classified briefing rooms where these decisions are made. What we can observe is behavior, and the behavior, the pattern of coordinated activation across multiple nations and agencies, that's data. That's information we can assess and evaluate even without access to the reasoning behind the decisions. Now let's talk about the X-ray detection, because this is where observational astronomy meets genuinely unprecedented territory. JAXA's XRISM satellite, a sophisticated X-ray observatory launched specifically to study high-energy phenomena in space, turned its instruments toward 3I Atlas from November 26th through November 28th. 77 hours of continuous observation, nearly 3 full days of collecting X-ray photons, building up signal from what everyone expected would be a faint source at best, possibly no detection at all because interstellar objects don't typically produce X-rays at levels detectable from Earth orbit. The result was published on December 3rd through the Astronomer's Telegram, a rapid communication system used by researchers to share time-sensitive astronomical observations that can't wait for traditional peer review. The findings are preliminary but clear. XRISM detected a faint X-ray glow from 3I Atlas, not just random noise, not just background radiation misattributed to the comet, a genuine signal, excess emission above baseline, coming from the location of 3I Atlas, with spectral characteristics that indicate real physical processes occurring in the object's vicinity. The spectrum, the breakdown of which X-ray wavelengths were detected at what intensities, shows excess emissions of carbon, nitrogen and oxygen beyond background levels. These elements aren't surprising in themselves. Comets are known to contain carbon-bearing molecules, nitrogen compounds, oxygen-rich ices. What's surprising is that these elements are producing X-ray emissions at detectable levels, that whatever process is exciting these atoms is energetic enough to strip away electrons and produce the high-energy photons that XRISM measured. Now, X-ray emission from comets isn't entirely unknown. Since 1996, researchers have understood that a process called solar wind charge exchange can produce X-rays when the sun's charged particle output, the solar wind streaming outward at hundreds of kilometers per second, interacts with a comet's gas cloud. The neutral atoms in the coma, the atmosphere of gas surrounding the nucleus, can interact with highly charged ions in the solar wind. Electrons transfer between the neutral atoms and the ions, and that transfer releases energy as X-ray photons. It's a well-understood mechanism, observed in multiple solar system comets, documented extensively in the scientific literature. But here's what makes 3I Atlas different, what makes this detection genuinely unprecedented. Neither Oumuamua nor Borisov, the two previous confirmed interstellar visitors, were ever detected in X-rays. Oumuamua showed no activity at all, no coma, no outgassing, nothing that would produce the neutral gas cloud necessary for charge exchange. Borisov did show cometary activity, a visible coma and tail, composition similar to solar system comets. But X-ray observations pointed at Borisov detected nothing. Either the emission was too faint, or the geometry was wrong, or something about Borisov's composition or activity level made X-ray production inefficient. 3I Atlas is the first interstellar object ever detected in X-rays. That's the headline. That's the genuinely new observation that adds to the growing list of ways this object is behaving differently than anything we've seen before. And when you combine that with everything else, with the trajectory precision and the geometric emissions and the anti-tail and all the other anomalies we've discussed in previous coverage, the X-ray detection becomes another data point in a pattern that grows more difficult to explain through conventional frameworks with each new observation. The XRISM team's announcement triggered immediate response. Research groups around the world are planning follow-up observations. Chandra X-ray Observatory, NASA's flagship X-ray telescope, has reportedly been allocated time to observe 3I Atlas. XMM Newton, ESA's X-ray Observatory, is also targeting the object. The goal is to confirm XRISM's detection, to refine the measurements, to study how the X-ray emission changes as 3I Atlas moves farther from the Sun and activity potentially declines. Because if the X-rays persist even as the object recedes, if the emission doesn't scale with solar distance the way charge exchange predicts, that would suggest additional energy sources, mechanisms beyond just solar wind interaction. And this is where Avi Loeb's recent media appearances become relevant, because Loeb has been arguing consistently and passionately that the scientific community needs to approach 3I Atlas with genuine open-mindedness, with willingness to follow evidence even when it leads to uncomfortable conclusions. In an interview with Chris Cuomo, Loeb laid out his perspective on how science should handle anomalous observations. The foundation of science is the humility to learn, not the arrogance of expertise, Loeb said. And I see science as the privilege of maintaining your childhood curiosity. I haven't changed much since the time I was a kid. That framing, science as maintaining childhood curiosity, resonates because it highlights what's often lost in professional scientific practice. Children ask questions without fear of appearing ignorant. They wonder about everything, approach the world with genuine openness to discovery. Professional scientists, constrained by career pressures and peer judgment, and the need to maintain credibility, often lose that openness. They become invested in existing frameworks, in theories they've built careers around, in explanations that are safe and conventional rather than risky and novel. Loeb continued, "My colleagues are making two mistakes. One, they lecture to the public what the public should know, and that's why the public sees science as an occupation of the elite, because it feels like a teacher in a classroom telling the students what they need to know, and you know very often that teacher doesn't know what they're speaking about. Things that were declared by science one way end up being a different way. The mistake that my colleagues are making is they pretend to know the answer. They pretend to know that this is a comet and they tell the public that." He called out specific individuals by name, the NASA administrator, commentators in the UK, people declaring with confidence that 3I Atlas is definitely a comet, definitely natural, definitely explainable through conventional frameworks. And Loeb's critique is pointed. None of these people is doing any scientific research. They haven't written a single scientific paper. They haven't looked at the evidence. They haven't analysed it. They just say what they think it is. And that's a big mistake. Whether you agree with Loeb's assessment of 3I Atlas, whether you find the artificial hypothesis compelling or absurd, his methodological point stands. Science requires humility about uncertainty. It requires honest acknowledgement of what's known and what isn't, what's explained and what remains mysterious. and it requires openness to possibilities that might seem unlikely, but that fit the evidence better than conventional explanations do. Dismissing hypotheses without examining evidence, declaring conclusions without analysis, that's not science. That's dogma masquerading as expertise. The takeaway extends beyond 3i Atlas. In our daily lives, the lesson applies universally. Stay open-minded, stay curious, always ask questions. Children are naturally filled with curiosity, but somehow along the way in adulthood that fades. We learn to accept conventional wisdom, to trust authority, to stop questioning because questioning feels uncomfortable or risky or socially inappropriate. But the greatest discoveries, the most important advances in human understanding, have come from people who kept questioning, who maintained that childlike curiosity, who asked why and how and what if, when everyone around them had already decided the answers. Science at its best brings that curiosity back. It should reward asking questions rather than punishing it. It should celebrate uncertainty and mystery as opportunities for discovery rather than embarrassments to be hidden. The fact that 3i Atlas raises questions we can't immediately answer, that it exhibits behaviours we don't fully understand, that's not a problem. That's the most exciting thing about it. That's why it matters. Because in the space between what we know and what we observe, in that gap where theories don't quite fit and explanations remain incomplete, that's where new understanding grows. Now let's get into the details of what XRISM actually detected, because the technical specifics matter for understanding why this observation is significant. X-ray astronomy is challenging. X-rays don't penetrate Earth's atmosphere effectively, so observations require space-based telescopes. And X-ray sources in space are typically either extremely hot, like the coronae of stars where temperatures reach millions of degrees, or extremely energetic like accretion disks around black holes, where matter reaches relativistic velocities before being consumed. Comets are neither hot nor energetic in those senses. They're cold, icy bodies warmed only by sunlight, moving at speeds measured in kilometers per second, not fractions of light speed. The X-ray emission XRISM detected is faint, right at the edge of detectability, which is why it required 77 hours of integration time to build up sufficient signal. But it's there. The spectrum shows emission lines characteristic of highly ionized carbon, nitrogen, and oxygen. These are atoms that have lost multiple electrons that exist in high-energy states that decay by emitting X-ray photons. The intensities of these emission lines, the relative brightness at different wavelengths, can be compared to models of what charge exchange should produce. And according to preliminary analysis, the observed spectrum is broadly consistent with charge exchange, but with some puzzling features. The nitrogen emission is stronger than expected relative to oxygen. The carbon lines show hints of multiple ionization states that don't quite match standard solar wind composition. These could be explained by variations in 3i Atlas's coma composition, by differences in how the object's gas cloud is structured compared to typical comets, or they could indicate additional processes beyond pure charge exchange, contributions from other energy sources that aren't accounted for in the models. Follow-up observations will be crucial. If Chandra and XMM Newton confirm the detection and refine the spectroscopy, if the emission lines can be measured more precisely, then models can be tested rigorously. Does the spectrum match charge exchange predictions exactly? Are there deviations that require additional explanations? Does the emission vary on short timescales suggesting transient energy releases rather than steady-state processes? All of these questions can be addressed with better data, and that data is being collected right now as multiple X-ray observatories target this unprecedented object. But the X-ray detection, significant as it is, isn't the only new development changing our understanding of 3i Atlas. There's the anti-tail situation, which has evolved in ways that deepen the mystery rather than resolving it. You've seen the images by now if you've been following this story. That sunward-facing structure, extending from the nucleus toward the sun rather than away from it, violating every intuitive expectation about how cometary tails work. Solar radiation pressure and solar wind should push material away from the sun. That's basic physics. That's how we've understood comets for centuries. Tails point away from the sun, always, regardless of the comet's direction of motion through space. 3i Atlas's anti-tail refuses to follow that rule. The latest Hubble Space Telescope image, captured on November 30th, shows the feature extending about 60,000 kilometers sunward from the nucleus. That's enormous. That's a structure large enough to dwarf Earth, maintained somehow against the forces that should disperse it. And Hubble's resolution allows us to see internal structure, variations in brightness along the anti-tail, suggestions of collimation, of geometry that's not just a random spray of particles but an organised flow. But here's where things get genuinely strange, where observations shift from mysterious to potentially significant. Dr. Sebastian Voltmer, an astrophotographer working from Utah, captured fresh images on December 1st, the day after Hubble's observation. He's been monitoring 3I Atlas throughout its perihelion passage, building a time series of images that document how the object's appearance changes. And what his December 1st images show is unexpected. The main anti-tail, the overall structure is fading. The brightness is dropping. That's expected behaviour. 3I Atlas is now moving away from perihelion, getting farther from the Sun with each passing day, receiving less solar heating, presumably experiencing declining outgassing rates as activity winds down. Everything should be getting dimmer. Every feature should be fading as the comet recedes and activity decreases. But the sunward jet, that specific component of the anti-tail pointing directly at the Sun, it's doing the opposite. It's getting larger. It's getting brighter. As the rest of the coma fades, as normal cometary activity declines, this one specific feature is intensifying. That's not how comets work. That's not predicted by any model of cometary outgassing and dust emission. It's anomalous. It's behaviour that demands explanation, and that doesn't have an obvious natural explanation within conventional cometary physics. Multiple interpretations are possible. Perhaps there's a vent on the nucleus that happens to be oriented toward the Sun, and as other vents shut down with declining solar heating, this one particular source continues or even increases activity. But that would require remarkably specific geometry, a vent positioned such that its output appears collimated directly sunward from Earth's viewing angle. And it would require that vent to be fed by volatile ices that sublimate more readily now, post-perihelion, than they did during perihelion when temperatures were higher. That's backwards. That's not how sublimation works thermally. Another possibility is that we're seeing effects related to changing geometry. As 3I Atlas moves along its orbit, as Earth's position changes, the viewing angle shifts. Features that were edge-on might become more face-on, increasing their apparent brightness without any actual change in physical emission. But this explanation requires careful geometric modelling to verify, and preliminary analysis suggests the brightening is too large to be purely geometric. Something about the physical emission from that sunward feature appears to be increasing, not just appearing brighter due to angle changes. Or, and this is where conventional explanations start to strain, the brightening could indicate active thrust. If the sunward feature is exhaust from a propulsion system, if 3I Atlas is still making trajectory adjustments post-perihelion, then we'd expect to see exactly this pattern. Most features fade as natural activity declines, but artificial thrust, controlled propulsion, that would operate according to mission requirements rather than thermal constraints. If the object needs to make a burn, needs to adjust velocity, the plume would be visible, regardless of whether natural outgassing is increasing or decreasing. This connects directly to what Avi Loeb discussed in his interview about probability and risk assessment. Loeb made an analogy to how intelligence agencies handle terrorism threats. Even if you assess probability as low, if you say there's only a 1% chance of a terrorist attack, you don't dismiss it. You don't ignore it because 99% confidence suggests it won't happen. The implications are too large. The consequences, if you're wrong, are too severe. So you take the 1% scenario seriously. You allocate resources. You prepare responses. You treat low probability, high impact scenarios with appropriate gravity. Loeb applies the same logic to 3I Atlas. Even if we assign a small probability that it might be a technological gadget, the implications are huge, and therefore we must take it seriously, he argued. Scientists, he suggested, are making a mistake by dismissing the artificial hypothesis based on probability arguments alone. Scientists would say, 99% I'm confident that it will not happen, therefore I will dismiss and ridicule any discussion about the 1% probability that it's something else. But that's not how risk assessment works when stakes are high. We know from very respectful public servants that this is not the right approach, Loeb continued. What you need to do, because of the large implications, you have to take it seriously. And there is a lot of money in the intelligence agencies dealing with black swan events. These are events that have low probability, but you must consider them seriously because of the implications. Black swan events, the term popularized by Nassim Taleb, refers to rare occurrences that have massive impact precisely because they're unexpected, because conventional thinking dismisses them until they happen and reshape everything. Is 3I Atlas a black swan event? Is this the moment when humanity's assumptions about cosmic solitude get overturned? When contact happens not through radio signals from distant stars, but through physical objects passing through our solar system? Or is it an unusual but ultimately natural comet that's teaching us about cometary diversity, but not fundamentally changing our place in the universe? The probability assessment matters less than the preparedness. If there's any reasonable chance that this object represents something beyond natural processes, then taking it seriously, studying it intensively, preparing for various scenarios, that's not alarmism. That's prudent risk management. And this brings us to one of Loeb's most provocative recent proposals, one that could explain why space agencies are suddenly coordinating defense drills and sharing classified data. Rather than 3I Atlas being a single object, Loeb suggests there may be multiple smaller companions moving alongside it. A swarm of objects, smaller pieces, potentially fragments that separated from the main body, or possibly independent entities travelling in formation. These companions would be sitting slightly closer to the Sun than the main body, trailing tens of thousands of kilometres behind in the orbital path. If such a swarm exists, if there are multiple objects rather than just one, that fundamentally changes the tracking problem. Monitoring one interstellar visitor is challenging enough. You need to measure position precisely, refine trajectory calculations continuously, characterize composition and activity level, all while the object moves at high velocity through space. But tracking multiple independent bodies, each potentially following slightly different trajectories, each exhibiting their own activity patterns, that requires orders of magnitude more observational resources. You need faster sensor systems capable of distinguishing multiple sources in close proximity. You need wider satellite coverage to maintain custody of all targets simultaneously. You need more agile response strategies that can adapt to changing configurations as the swarm components move relative to each other. The coordination between space agencies, the sharing of classified tracking data, the acceleration of defense drills, all of this makes more sense if decision-makers think they might be dealing with multiple objects rather than just one. Has such a swarm been detected? Official announcements don't mention it. Public observations from ground-based telescopes show one primary source, with extended structure that could be interpreted as coma and tails. But classified tracking systems, assets with resolution and sensitivity beyond what's publicly available, they might see more. They might have detected multiple discrete sources, smaller objects in the vicinity of the main body, components that aren't visible in public data, but that show up clearly when you have the right instruments looking from the right angles. This is where the classification barrier becomes frustrating. If military or intelligence satellites have detected companion objects, if there's evidence of a swarm configuration, that information would be highly classified. It would reveal capabilities that agencies want to keep secret, but it would also be profoundly important for scientific understanding of what 3I Atlas represents and what appropriate response measures look like. The gap between what's publicly known and what's classified could be enormous, leaving academic researchers and the public operating with incomplete information while policy decisions are made based on data we can't access. Loeb has been explicit about wanting access to government data. In his interview, he stated, if they have any data that they cannot understand, that they know is not related to adversarial nations, because they're witnessing some performance of objects that cannot be mimicked by the technologies we possess, then they should let scientists like myself help them, because it's not their jurisdiction to figure out what lies outside the solar system. So I would very much hope that if they have anything like that, they would share it with me. That appeal hasn't been answered publicly. Whether Loeb or other researchers have been granted classified access behind the scenes, we can't know. But the fact that EON updated protocols to allow temporary use of classified data for non-standard hyperbolic bodies suggests movement toward greater information sharing, at least among authorized recipients. Whether that data will ever be released to the broader scientific community or to the public remains uncertain. But given the coordination we're seeing, given the sharing between nations that typically guard capabilities jealously, something significant is driving cooperation. There's also a temporal element to this story that hasn't received sufficient attention. Between March and April of 2026, Earth will orbit through the region of space where 3I Atlas was located during its perihelion passage in late October and early November 2024. Think about what that means. For weeks, maybe months around perihelion, 3I Atlas was vigorously outgassing, ejecting jets of material producing that massive coma and those anomalous tails. All that material, gas and dust and whatever else the object was emitting, that doesn't just disappear. It spreads out along the object's orbital path, creating a diffuse trail of debris that persists even after 3I Atlas itself has moved on. When Earth crosses that region, when our planet passes through the space that 3I Atlas occupied months earlier, we might encounter that debris. The density is probably very low. We're not talking about a hazardous asteroid field or anything that poses collision risk. But instruments on Earth, atmospheric sensors, satellites in orbit, they might detect particles or compounds from 3I Atlas's coma. We might capture actual samples of material from an interstellar visitor, not through deliberate sample return mission, but through fortuitous intersection with debris trails. Scientists will be watching that window very closely. Ground-based sensors that monitor atmospheric composition, satellites with particle detectors, even the International Space Station, if it's still operational in March-April 2026, could potentially collect samples as Earth passes through the debris zone. The composition of that material, the isotopic ratios, the molecular species present, all of that would provide data about 3I Atlas that can't be obtained from remote observation. It's a natural experiment, a free sample return mission courtesy of orbital mechanics. But there's another possibility, one less benign. If 3I Atlas contains artificial components, if it's been deliberately shedding material, if what we've been interpreting as natural outgassing is actually intentional deployment of smaller probes or sensors, then Earth's passage through the debris zone becomes potentially significant for different reasons. We're not just collecting cometary dust, we're potentially intercepting technology, encountering objects that might be designed to interact with planets passing through the region. That's speculation, certainly, but it's speculation that matches observed behavior, that fits with the pattern of anomalies, that explains why space agencies might be conducting defense drills timed to coincide with this object's closest approach. And closest approach is happening soon, 8 days from the date of this script, December 19th, when 3I Atlas will be at minimum distance from Earth. Still far away by terrestrial standards, over 100 million kilometers, nothing like the close passes that near-Earth asteroids sometimes make. But close by interstellar standards, close enough that ground-based telescopes will have their best views, that spectroscopy and photometry and all the observational tools we use to characterize objects in space will work at peak effectiveness. Close enough that if anything unusual happens, if the object does something unexpected, we'll see it clearly. What are researchers watching for? Changes in trajectory that can't be explained by gravitational forces, sudden brightening or dimming that doesn't match models of cometary activity, spectroscopic signatures that indicate new composition or new emission processes, geometric changes in the coma structure, in those jets and features that already look anomalous, radio emissions, X-ray variations, any signal that suggests activity beyond passive reflection of sunlight and routine sublimation of ices. Every telescope that can reach this object will be pointed at it. Every sensor that might detect something unusual will be active, and all that data, all those observations from dozens of instruments in multiple wavelengths, will flow into analysis pipelines that are now running continuously, trying to build comprehensive understanding before the window closes and 3I Atlas moves beyond effective observation range, and we're left with whatever we managed to collect during its passage, and a lifetime of questions about what we might have missed if only we'd looked more carefully or thought to measure the right thing at the right time, which is why this moment matters, why these 8 days until closest approach represent an opportunity that won't come again, at least not with this object, at least not in our lifetimes, to observe something from beyond in detail and hopefully to understand what it represents, and what it means for our species and our understanding of what's possible in a universe that keeps proving itself stranger than our theories predicted. Because understanding what we're looking at requires more than just observing. It requires context. It requires comparing what we see with what we've seen before, recognizing patterns, identifying deviations from those patterns that signal something genuinely new. And with 3I Atlas, the deviations are piling up faster than conventional explanations can accommodate them. Every new observation seems to add another piece that doesn't quite fit, another measurement that falls just outside expected ranges, another behavior that makes sense individually but collectively paints a picture that's increasingly difficult to reconcile with the simple story of a natural comet passing through. Let's dig deeper into the X-ray detection, because the technical details reveal why this observation matters so much. When XRISM pointed its instruments at 3I Atlas, the team knew they were attempting something ambitious. X-ray emission from comets, even when it occurs through well-understood charge exchange processes, is faint. You're not dealing with a bright X-ray source like a neutron star or an active galactic nucleus. You're dealing with subtle glow produced by relatively gentle interactions between solar wind ions and cometary neutrals. The photon flux, the number of X-ray particles reaching the detector per unit time, is low enough that you need large collecting areas and long integration times to build up statistically significant signal. XRISM has advantages for this kind of observation. Its main instrument, called Resolve, is a microcalorimeter, a type of detector that measures not just whether an X-ray photon arrived, but precisely how much energy it carried. That energy measurement translates directly to wavelength, to spectral information about which emission lines are present and how bright they are. For studying comets, where you want to identify specific elements and their ionization states, spectral resolution is crucial. You can't just detect a generic X-ray glow and call it a day. You need to break that glow into components to see which atoms are emitting at which energies. The 77 hours of observation weren't continuous. XRISM operates in low Earth orbit, which means it cycles through periods of visibility and occultation, times when it can see 3I Atlas versus times when Earth blocks the view. But over the 3-day period from November 26th through 28th, the team accumulated enough exposure time to detect signal, and when they processed the data, when they extracted the spectrum from the raw photon counts, the result was clear enough to publish. Carbon emission lines at characteristic energies around 0.3 to 0.5 keV. Nitrogen lines in a similar range. Oxygen lines slightly higher in energy, all of them showing intensity above background, all of them consistent with highly ionized states that emit X-rays when electrons recombine and cascade down to lower energy levels. The published spectrum, available through the astronomer's telegram for anyone to examine, shows these features clearly, but it also shows something else, something that hasn't been emphasized in most coverage, but that's visible in the data. The continuum, the smooth underlying X-ray emission that fills in between the bright emission lines, is slightly elevated compared to what pure charge exchange models predict. It's not a huge excess, it's within the uncertainties of the measurement, but it's there, a hint that maybe there's additional emission beyond just the line radiation from recombination. What could produce continuum X-ray emission from a comet? One possibility is bremsstrahlung, radiation produced when charged particles are decelerated by electric fields. If there's a population of electrons in the coma with higher energies than the solar wind typically provides, those electrons could produce bremsstrahlung as they scatter off ions. But that requires an acceleration mechanism, some way to boost electron energies beyond thermal values. Solar wind electrons aren't generally energetic enough. You'd need something else, some local acceleration process. Another possibility is scattering. X-rays from the sun could scatter off dust particles in the coma, producing a faint continuum. But the geometry matters. For efficient scattering, you need the right particle sizes and compositions, and the scattered flux depends on how much solar X-ray emission exists in the first place, which varies with solar activity. During the November observations, solar X-ray output was moderate, not particularly enhanced, which makes scattered solar X-rays an unlikely dominant contributor. Or, and this is where we venture into more speculative territory, the continuum could indicate thermal emission. If there are regions in or near the nucleus that are genuinely hot, not just warmed by sunlight to a few hundred Kelvin but actually hot to temperatures of millions of degrees, those regions would emit thermal X-rays across a broad spectrum. But what would create such temperatures? Natural comets don't have internal heat sources capable of reaching those extremes. Radioactive decay produces heat, certainly, but nowhere near enough to generate X-ray temperatures. You'd need nuclear reactions, plasma processes, something fundamentally beyond the gentle sublimation and dust emission that defines cometary activity. The XRISM team's published analysis doesn't speculate about these possibilities. They present the spectrum, note the emission lines, mention that the overall flux is consistent with charge exchange, and acknowledge that higher spectral resolution and longer exposures would help refine the analysis. That's appropriate scientific caution. You don't make extraordinary claims based on preliminary data. You present what you found, acknowledge uncertainties, and call for follow-up observations, which is exactly what's happening. Chandra has now observed 3I Atlas. The results haven't been publicly released yet. XMM Newton observations are planned or possibly already executed. And when those results become available, when multiple independent datasets all converge on the same spectral features, confidence in the X-ray detection will solidify. But even with current data, even with just the XRISM observations, we can say definitively that 3I Atlas is the first interstellar object ever detected in X-rays. That fact alone is significant. It means this object is producing X-ray emission through some mechanism, whether conventional charge exchange or something more exotic, at levels sufficient to be detected across interplanetary distances. And it means that whatever processes are occurring in the coma of 3I Atlas, they're energetic enough to create the high ionization states and high-energy photons that X-ray astronomy measures. Now let's return to the anti-tail situation, because new observations are continuing to come in, and the picture keeps evolving in ways that deepen the mystery rather than resolving it. The images from Sebastian Voltmer on December 1st showed the sunward jet brightening, even as the rest of the structure fades. That was striking enough. But there's more. Additional observations from December 3rd and 4th, captured by multiple amateur astronomers using different equipment at different locations, show the same pattern. The forward-pointing feature is not just persisting, it's maintaining brightness, or even slightly increasing while everything else about 3I Atlas dims. This is extraordinarily unusual behavior. Let's think about what should happen as a comet moves away from the Sun after perihelion. Solar heating decreases with the square of distance. As 3I Atlas recedes, as it gets farther from the Sun, it receives less energy per unit area. Less heating means less sublimation. Less sublimation means less gas production. Less gas means smaller coma, dimmer tail, declining activity across the board. Every feature should be fading together, following predictable curves that match the decrease in solar energy input. But the sunward jet isn't following that pattern. Its brightness, measured in multiple images by multiple observers, is essentially flat over the period from December 1st through December 4th. That's 3 to 4 days of no significant dimming, even as the comet moved several million kilometers farther from the Sun. The flat-like curve implies that whatever's producing the sunward jet isn't responding to solar heating in the normal way. It's maintaining output independent of declining solar energy, which means it must have some other energy source or some reservoir of volatiles that's depleting more slowly than surface ices. Or, and this is the interpretation that can't be dismissed without evidence, the sunward jet is exhaust from active propulsion that's still firing, that's still adjusting the trajectory, that's operating according to mission requirements rather than thermal constraints. If you're trying to fine-tune an approach to Jupiter's Hill radius, if you need to make small velocity changes to optimize the encounter geometry, you'd fire thrusters during the approach phase, and we'd see exactly what observers are seeing, a directed emission feature that doesn't fade with solar distance because it's not driven by solar heating in the first place. Testing this hypothesis requires more than just images. It requires precise astrometry, position measurements accurate enough to detect small trajectory changes. Fortunately, multiple professional observatories have been conducting exactly these measurements. The data isn't all public yet. Analysis takes time, but preliminary results that have been shared in informal channels suggest that 3I Atlas's trajectory is still showing small residuals, deviations from pure gravitational motion that require non-gravitational forces to explain. That's not surprising for any active comet. But the magnitude and direction of these residuals, the way they correlate with the observed jet activity, that will be crucial for distinguishing between natural outgassing and active propulsion. If the non-gravitational acceleration points along the sunward jet direction, if the forces needed to explain the trajectory deviations align with the visible emission feature, that's evidence for directed thrust. Natural outgassing jets point in various directions based on where vents are located on the rotating nucleus. The net force is a vector sum of all the individual jets, and it typically points at some angle that doesn't correspond to any single visible feature. But artificial thrust would be aligned with exhaust plumes. The emission you see would be directly connected to the force being applied, and that correlation, if it's confirmed in the data, would be very difficult to explain naturally. There's also the question of composition changes. Spectroscopy of 3I Atlas has been ongoing throughout its passage. Multiple teams have obtained spectra at different dates, tracking how the emission lines evolve as conditions change. Early spectra, taken when the comet was approaching perihelion, showed strong water emission, carbon-bearing molecules like CN and C2, all typical cometary species. Post-perihelion spectra are showing some differences. The water is still there, but relatively weaker. Carbon monoxide emission has increased proportionally, and there are hints, not yet confirmed but suggestive, of emission lines that don't match standard cometary molecules. One line that keeps appearing in multiple spectra, weak but persistent, is at a wavelength around 520 nanometers. That's green, visible to the naked eye if it were bright enough. But no common cometary molecule emits strongly at exactly that wavelength. Oxygen can produce green emission under certain conditions, specifically when it's in an excited state that's uncommon in typical cometary environments. Getting oxygen into that excited state requires either high-energy radiation beyond what sunlight provides, or collisions with energetic particles. Either way, it suggests something unusual about the energy environment in 3I Atlas's coma. Another spectroscopic oddity is the ratio of different, carbon-bearing molecules. CN, cyanogen, is usually one of the brightest emission features in cometary spectra. It comes from the breakup of larger organic molecules, HCN and others, when they're exposed to sunlight. C2, diatomic carbon, is another common feature produced through similar photochemistry. The ratio of CN to C2 brightness is normally fairly consistent across comets, falling within a well-defined range that reflects the parent molecule abundances in cometary ice. 3I Atlas's CN to C2 ratio is outside that range. It's shifted toward more CN relative to C2 than typical comets show. That could mean the parent molecule mix is different, that interstellar comets form with different organic chemistry than solar system comets do. Or it could mean that the photochemistry is unusual, that something about how sunlight interacts with the coma is producing different breakdown pathways than normal. Either interpretation is interesting, either suggests that 3I Atlas is genuinely different in composition or environment from the comets we're familiar with. These spectroscopic details might seem esoteric, might feel like technical minutiae that don't matter for the bigger questions about whether the object is natural or artificial. But they matter enormously, because composition determines behavior. The specific molecules present, the abundances of different elements, the isotopic ratios that reveal formation conditions, all of this information constrains models of what 3I Atlas is and where it came from. If the composition is clearly cometary, if it matches expectations for ices formed in protoplanetary disks, then natural origin becomes more likely regardless of trajectory oddities. But if the composition is anomalous, if it doesn't fit any natural formation scenario, then alternative explanations gain credibility. And here's where the conversation intersects with what Avi Loeb has been advocating for publicly. Loeb isn't just saying this might be aliens, he's saying we need to look at all the evidence, collect more data, and follow that data wherever it leads rather than dismissing possibilities based on preconceived notions. In his interview with Cuomo, Loeb emphasized that even low probability scenarios deserve serious investigation when implications are significant. There is a lot of money in the intelligence agencies dealing with black swan events, he noted. These are events that have low probability, but you must consider them seriously because of the implications. That framework, treating unlikely but high-impact scenarios with appropriate seriousness, is exactly what space agencies appear to be doing with these coordinated drills. They're not announcing that 3I Atlas is a threat. They're not claiming it's artificial. But they're preparing for scenarios that might seem unlikely, but that would be catastrophic if they occurred without preparation. What if the object does something unexpected? What if it releases smaller probes? What if it changes trajectory toward Earth rather than continuing toward Jupiter? These scenarios might each have low individual probability, but collectively, the probability that something unusual happens might not be as low as conventional thinking suggests. And this is where Loeb's proposal about multiple objects, about a potential swarm configuration, becomes critically important. If 3I Atlas is accompanied by smaller bodies, if there are companions travelling in formation, the tracking problem changes fundamentally. You're not just watching one object follow a predictable trajectory, you're monitoring a system with multiple components that might have independent propulsion, that might be capable of manoeuvring relative to each other, that might deploy or separate at any time, creating new targets that need tracking. Has evidence of such companions been detected? Publicly, no. No announcements have been made about multiple objects. Ground-based images show one primary source with extended structure that looks like coma and tails, but those images have resolution limits. Smaller objects separated by even tens of thousands of kilometers from the main body might not be distinguishable in ground-based data, especially if they're not actively outgassing, if they're dark objects that don't reflect much sunlight or emit their own light. You'd need high-resolution imaging from space-based platforms to detect them, and here's what we know. Classified tracking systems do have that resolution. Military surveillance satellites designed to watch for missile launches, to track spacecraft, to monitor orbital activity. These assets have imaging capabilities that far exceed what's publicly available. If such systems have been tasked to observe 3I Atlas, and given the defense drill coordinations there's every reason to think they have been, they might very well have detected things that haven't been disclosed. Small, dark objects near the main body, pieces that separated during the perihelion passage, independent movers with trajectories that differ slightly from the primary. The update to IARMUN protocols, specifically allowing classified data sharing for non-standard hyperbolic bodies, could be a response to exactly this situation. If military or intelligence assets detected companions, if there's classified data showing a more complex picture than public observations reveal, sharing that data with civilian space agencies makes sense. It allows them to refine models to understand what they're tracking, to prepare responses that account for the full complexity of the situation, rather than just the simplified single-object scenario visible in public data. But that data sharing, if it's occurring, is happening behind closed doors. Researchers without security clearances, amateur astronomers contributing observations, the general public following this story, we're all operating with an incomplete picture. We see what ground-based telescopes can resolve. We get announcements about X-ray detections and trajectory updates. But if there's a classified layer of information, if military assets are seeing things we're not being told about, then the discussion we're having in public is necessarily limited and potentially misleading. Loeb has been explicit about wanting access to government data that might clarify these questions. If they have any data that they cannot understand, that they know is not related to adversarial nations because they're witnessing some performance of objects that cannot be mimicked by the technologies we possess, then they should let scientists like myself help them, he stated. That's a reasonable request. If tracking systems have detected anomalies, if there are observations that don't fit conventional explanations, the scientific community should have access to analyze those observations properly. The counter-argument, of course, is that releasing such data reveals capabilities that adversaries would exploit. If you publish high-resolution images from classified satellites, you tell potential enemies exactly what those satellites can see, what their resolution limits are, how they're being tasked. That information is operationally valuable. Keeping it secret maintains strategic advantage. And from a military perspective, maintaining that advantage takes priority over scientific transparency, especially when there's no immediate threat, when the object is following a trajectory that doesn't endanger Earth. But that calculation changes if the object isn't following a simple trajectory, if there are companions, if the situation is more complex and potentially more significant than a single natural comet passing through. At some point, the value of scientific analysis exceeds the cost of revealed capabilities. Determining where that point is, when to prioritize transparency over secrecy, that's a judgment call being made by people we don't see in meetings we're not privy to. And we won't know if they made the right call until we see how the situation develops, until December 19th arrives, and closest approach happens, and we either observe something that demands immediate response, or we confirm that 3I Atlas is following a predictable gravitational path, and the mystery, while remaining, will at least not represent an immediate operational concern requiring the kind of coordinated multinational response that these defense drills suggest might be necessary. Which brings us to the critical window, the period we're entering right now, when 3I Atlas reaches its closest point to Earth, and every instrument capable of observing it will be trained on this object with maximum intensity. December 19th isn't just a date on a calendar. It's the moment when observational geometry becomes optimal, when angular separation between Earth and 3I Atlas reaches minimum, when resolution limits relax and detail becomes visible, that's hidden when the object is farther away. For researchers who have been tracking this visitor for months, for observers who have documented every phase of its passage, this is the culmination, the best chance to see clearly before the object recedes beyond effective observation range. Think about what closest approach means practically. At minimum distance, roughly 140 million kilometers, 3i Atlas will still be far by terrestrial standards. It's not a close pass like some asteroids make, sweeping within a few million kilometers or even closer. But it's near enough that parallax effects become measurable, that stereoscopic observations from different locations on Earth can triangulate distance with precision. It's near enough that spectroscopy works at peak efficiency, collecting maximum photons per unit time, building signal-to-noise ratios that allow detection of faint features invisible when the object was more distant. And it's near enough that any changes in brightness, any variations in activity level, any unexpected behaviors will be immediately obvious rather than buried in observational noise. The observation campaign for December 19th has been coordinated months in advance. Major observatories around the world have allocated time. Hubble Space Telescope is scheduled for multiple exposures. The James Webb Space Telescope, though primarily designed for infrared observation of distant objects, has been tasked to observe 3i Atlas in wavelengths, where its sensitivity might reveal thermal emission patterns invisible to optical telescopes. Ground-based facilities from Mauna Kea to the Atacama Desert, from the Canary Islands to South Africa, all have observing programs ready to execute. The global distribution ensures continuous coverage as Earth rotates, as different sites gain and lose visibility, maintaining persistent observation across the critical 24-48-hour window, centered on closest approach. Amateur astronomers are participating as well. Networks of dedicated observers with their own equipment, ranging from modest backyard telescopes to sophisticated private observatories, have organized campaigns to collect images and photometry that will supplement professional observations. This distributed approach has advantages. While professional facilities have superior instruments and larger apertures, they're limited in number and availability. Amateur networks provide redundancy, temporal coverage, and sheer volume of observations that no centralized system can match. And in cases where something transient occurs, where an outburst or sudden change happens on timescales of hours, having hundreds of eyes watching increases the probability that someone captures the event. What specifically are observers looking for? The checklist is long and detailed. First priority is astrometry, position measurements that refine the trajectory and allow detection of any deviations from gravitational predictions. Multiple independent position measurements from different sites, all time-stamped precisely, will be combined to build an orbital solution accurate to within thousands of kilometers. That accuracy is crucial for detecting non-gravitational forces. If 3i Atlas is under any form of propulsion, if it's making trajectory corrections, those corrections will show up as systematic residuals in the astrometric solution, deviations that can't be explained by gravity alone. Second priority is photometry, brightness measurements in multiple wavelength bands, optical photometry in standard filters, B-band blue, V-band visual, R-band red, I-band infrared, building a color profile that reveals how the object reflects and emits light at different wavelengths. That profile contains information about composition, about particle size distribution in the coma, about whether the nucleus has exposed ice or is covered in dark refractory material. Temporal variations in brightness, changes over hours or days, could indicate rotation, with different parts of the nucleus having different albedos. Or they could indicate changes in activity level, with outgassing increasing or decreasing on short timescales. Third priority is spectroscopy, and this is where closest approach provides maximum advantage. Spectral resolution depends on signal strength. The brighter the object, the more photons you collect, the finer you can divide the spectrum into narrow wavelength bins. At closest approach, with maximum brightness, spectroscopy can achieve resolution that reveals individual molecular emission lines with clarity. Researchers will be looking for known cometary molecules: water, carbon monoxide, carbon dioxide, methane, ammonia, hydrogen cyanide, all the species typically found in comets. But they'll also be scanning for unknowns, for emission or absorption features that don't match the standard catalogue, that hint at exotic chemistry or unusual processes. Fourth, polarimetry. Measuring the polarization of reflected light provides information about surface properties and dust characteristics that photometry alone can't reveal. Polarization depends on particle size, shape, and composition. Rocky particles polarize light differently than icy particles. Smooth surfaces produce different polarization signatures than rough surfaces. If 3i Atlas has metallic components, if there are regions with geometric structures rather than random particulate surfaces, polarimetry might detect them through anomalous polarization that doesn't fit cometry dust models. Fifth, infrared thermal imaging. The warmth of an object in space, its thermal emission in infrared wavelengths, reveals how efficiently it absorbs and radiates solar energy. That efficiency depends on surface properties, on albedo and thermal conductivity and emissivity. Measuring thermal emission allows calculation of temperature, which can be compared to models of what temperature should be based on solar distance and assumed properties. Deviations from predicted temperature could indicate internal heat sources, or unusual surface compositions, or geometric effects if the object has non-spherical shape with complex thermal properties. And sixth, though this is unlikely to succeed given the distance, radar probing. Active radar, where you transmit a signal and measure the echo, provides direct information about surface properties and three-dimensional shape that passive observation can't match. The Arecibo Observatory, before its collapse, could radar map asteroids at remarkable resolution, revealing surface boulders and craters invisible to optical telescopes. Remaining radar facilities, particularly the Goldstone Deep Space Network antenna, have capabilities but limited range. 3i Atlas will probably be too distant for effective radar, but attempts will be made. If even a weak echo is detected, if any signal comes back, it would provide constraints on surface reflectivity and roughness, invaluable for understanding the object's nature. All of this data, flowing in from multiple sources using multiple techniques, will be processed and analysed in near real time. Research teams are standing by to examine results as they arrive, to look for anomalies, to flag anything unexpected for immediate follow-up. This isn't a situation where data gets archived and analysed leisurely over months. This is active, responsive observation, where what you see in one measurement might determine what you observe next, where priorities shift based on emerging results, where the campaign adapts dynamically to what the object is actually doing rather than following a predetermined script. And underlying all of this, though not openly acknowledged in public communications, is the awareness that December 19th represents a decision point. If observations show nothing anomalous, if 3i Atlas behaves like a comet should behave, following gravitational trajectories and exhibiting normal outgassing consistent with solar heating, then the artificial hypothesis loses credibility. The mystery might remain about the trajectory precision and the geometric emissions and all the other oddities, but without new anomalies appearing during closest approach, the argument that this is just an unusual natural comet gains strength. Researchers can continue studying it as an interesting but ultimately conventional object, one that expands our understanding of cometary diversity, but doesn't fundamentally challenge our cosmic assumptions. But if observations do show anomalies, if something happens that can't be explained naturally, if the object does something that looks like deliberate action rather than passive response to forces, then the situation changes. The artificial hypothesis, currently speculative and controversial, would become the leading explanation, the framework that best fits all available evidence, and that shift would trigger responses beyond just scientific analysis. It would activate those coordination protocols we've been seeing rehearsed in the defense drills. It would require decisions about communication, about whether to attempt contact, about how to respond to confirmed artificial technology from beyond our solar system. That's the subtext beneath all the coordinated observation campaigns and defense exercises. December 19th is a test. Not a test we designed, not an experiment we control, but a natural test imposed by orbital mechanics and whatever 3i Atlas actually is. We're about to get data that will either support or refute the most extraordinary hypothesis in modern astronomy. And space agencies, governments, military organizations, they're all preparing for the possibility that the data supports rather than refutes, that we're days away from confirmation that fundamentally changes humanity's understanding of its place in the universe. Now let's talk about what happens after closest approach, because the story doesn't end on December 19th. Assuming 3i Atlas continues on its predicted trajectory, Assuming it doesn't do something unexpected that changes the entire situation, the object will proceed toward its encounter with Jupiter's Hill radius, that gravitationally stable region where it could theoretically park in a long-term orbit. That encounter is projected for early 2025, just weeks from now, and what happens during that encounter will be as significant as anything observed during closest approach to Earth. If 3I Atlas simply passes through Jupiter's Hill radius, if it continues on a hyperbolic trajectory that carries it out of the solar system without significant gravitational capture, then it behaves like a natural object should. Interstellar visitors on hyperbolic orbits don't get captured by planets during brief encounters. The velocities are too high, the energy too large. Capture requires either extremely precise geometry and velocity, conditions so specific that they occur essentially never by chance, or it requires active braking, deliberate reduction of velocity to match the planet's gravitational binding energy. Natural objects don't break, they pass through and keep going, but if 3I Atlas doesn't pass through, if observations in early 2025 show the object entering an elliptical orbit around Jupiter, or settling into a stable position at a Lagrange point, that would be extraordinary. That would be trajectory modification, on a scale that demands explanation. You can't wave hands about outgassing forces. You can't invoke random perturbations. Orbital insertion around a planet, especially when you're coming from interstellar space with hyperbolic excess velocity, requires propulsion. Significant sustained propulsion applied at precisely calculated times and directions to achieve the desired orbit. And that would be proof, definitive proof that this object is under intelligent control. Monitoring the Jupiter encounter will require different assets than the Earth. Closest approach. Jupiter is far, over 600 million kilometers from Earth at typical distances. Ground-based observation is still possible, but with reduced resolution. Space-based telescopes can observe, but with longer integration times to build adequate signal. The ideal platform would be something close to Jupiter, something in Jovian orbit that can watch the encounter from proximity. And here's where things get interesting. We do have assets near Jupiter. The Juno spacecraft has been orbiting the planet since 2016, studying its magnetosphere and internal structure. Juno's instruments aren't designed for tracking comets, but they could be retasked if necessary. They could provide observations from a vantage point unavailable to Earth-based systems. There's also the Europa Clipper mission, launched recently and currently en route to Jupiter. Its arrival timeline should place it in the Jovian system, around the time of 3I Atlas's Hill radius encounter. While its primary mission is studying Europa, Jupiter's ice-covered moon, the spacecraft has cameras and spectrometers that could observe 3I Atlas if mission planners decide the opportunity is worth the fuel expenditure for trajectory adjustments. Whether such retasking occurs, whether scientific priorities allow diversion from the primary mission, we'll know based on announcements in coming weeks. But there's another factor that hasn't been publicly discussed but that classified planning might address. If there really are rapid response capabilities, if those references in leaked documents to orbital insertion assets and classified spacecraft describe real hardware, then the Jupiter encounter would be when such assets get deployed. You wouldn't reveal classified capabilities for Earth observations when ground-based and conventional space telescopes can provide adequate data. But for Jupiter, where observation from Earth is marginal, and where potential orbital insertion by 3I Atlas would be the most significant event, using classified assets might be justified. They could maneuver close, collect high-resolution data, directly measure whether the object is actively thrusting, and provide intelligence that shapes policy decisions about disclosure and response. We won't know if this happens. By definition, classified assets operate without announcement. But if 3I Atlas does something extraordinary at Jupiter, if it enters orbit or deploys companions or exhibits behavior that proves artificiality beyond doubt, and if subsequently there are detailed observations released that couldn't possibly come from Earth-based or announced space telescopes, then we'll know retrospectively that something else was watching, that capabilities exist beyond what's publicly acknowledged, and that realization itself would be significant, confirming that space programs operate on multiple levels, with public missions serving as cover for or complement to classified activities that pursue different objectives. Now, circling back to that March-April 2026 timeframe, when Earth passes through the debris field left by 3I Atlas during perihelion, let's discuss what preparations are being made for that encounter. Space agencies are treating this as a scientific opportunity, a chance for direct sampling that doesn't require expensive spacecraft or years of planning. But they're also treating it seriously from a planetary defense perspective, asking questions about whether any of the debris could pose hazards, and ensuring monitoring systems are ready to detect anything unusual. The probability of hazard is extremely low. Even if 3I Atlas ejected large chunks during perihelion, even if there are meter-sized or larger fragments travelling along the orbital path, the density in space is such that Earth's cross-section, the area we present as a target, is tiny compared to the volume through which debris is distributed. The odds of actually hitting anything are vanishingly small, but small doesn't mean zero. And when you're talking about objects travelling at interstellar velocities, even small pieces carry enormous kinetic energy. A fragment the size of a basketball, if it hit Earth's atmosphere at 3I Atlas's velocity, would produce an airburst comparable to a small nuclear explosion. So monitoring is warranted. Not because impact is likely, but because the consequences if it happens would be significant enough to justify watching. Meteor detection networks, systems designed to spot fireballs and track atmospheric entry events, will be on alert during the March-April window. Infrasound sensors that detect shockwaves from bolides will be monitoring. Satellite-based systems that watch for bright flashes in Earth's atmosphere, originally deployed to detect nuclear tests but now used for fireball tracking, will have data reviewed carefully for any events during the debris field crossing. But the more interesting possibility isn't impact hazard, it's sample collection. If 3I Atlas shed material, if there are particles and dust spread along its orbital path, Earth's passage through that region means we'll intercept some of it. How much, and whether it's enough to detect and collect, depends on density and on how good our collection systems are. The International Space Station, if it's operational in March 2026, has exposure experiments with collection surfaces that could capture dust grains. Analysis of those surfaces after the encounter window might reveal particles of interstellar origin, material chemically or isotopically distinct from solar system dust. Ground-based collection is harder but possible. High-altitude aircraft equipped with sticky collection plates have been used to sample stratospheric aerosols, and some of those samples have been identified as likely interstellar grains based on isotopic anomalies. Similar collection efforts during the debris field crossing might yield samples. The challenge is distinguishing 3I Atlas material from the background of natural dust that's always present. You need isotopic analysis, looking for signatures that don't match anything from our solar system, that point to formation in different stellar environments. That's expensive and time-consuming analysis, but for material from an interstellar visitor, it's worthwhile. And then there's the more exotic possibility. If 3I Atlas is artificial, if it's been shedding technology rather than just natural coma material, Earth's passage through the debris field becomes a potential encounter with that technology. Imagine if some of what was ejected during perihelion was deliberate deployment, small probes or sensors designed to gather data or establish a presence in the inner solar system. Now imagine Earth passing through the region where those objects are drifting. We might intercept them, our satellites might encounter them. Detection systems might see them not as dust but as discrete objects with geometric shapes and electronic emissions. This scenario sounds like science fiction, but it's exactly the kind of low-probability, high-consequence event that Loeb and others argue deserves serious consideration. If there's any chance, any reasonable possibility, however small, that we might encounter artificial objects during the debris field crossing, then having detection systems active and ready makes sense. You don't need to believe it's likely. You just need to acknowledge that if it happens and you're not watching, you'll miss the most important opportunity in human history. The expected value calculation, probability times consequence, favours watching even when probability is assessed as very low. So what's actually being planned? Official statements emphasise scientific observation, sample collection, meteor monitoring, all conventional activities that sound reasonable and unalarming. But underlying that public framing, if the coordination we've seen with defence drills is any indication, there are probably classified preparations as well. Space surveillance systems will be at heightened readiness. Satellite operators will have protocols for responding to unexpected detections. Communication channels between civilian and military space agencies will be active, ready to share data quickly if something unusual is observed. All of this happens quietly, without announcements, without generating public concern, But it happens because the people making these decisions recognize that March-April 2026 represents a window when something could occur that requires rapid, coordinated response. There's also a psychological dimension to all of this that deserves attention. We're living through a period of sustained uncertainty about 3I Atlas. The object has been under observation for months. The anomalies have been accumulating. The artificial hypothesis has been gaining traction, despite strong institutional resistance, and now we're approaching critical decision points, moments when data will either confirm or refute the most extraordinary claims. That creates tension, it creates anticipation, and it creates vulnerability to both premature conclusions and denial of evidence. Human psychology doesn't handle prolonged uncertainty well. We want resolution. We want to know one way or the other, to settle the question so we can stop holding contradictory possibilities in our mind simultaneously. That pressure to resolve uncertainty can lead to premature acceptance of whichever explanation feels more comfortable or aligns with pre-existing beliefs. Natural explanation feels safer, fits better with the worldview that we're alone in the universe, doesn't require uncomfortable adjustments to fundamental assumptions, so there's psychological motivation to accept natural explanations, even when evidence doesn't fully support them, to dismiss anomalies as misunderstandings or artifacts rather than acknowledging they might indicate something genuinely unprecedented. Conversely, for those who are inclined toward believing in extraterrestrial visitation, who have pre-existing conviction that we're not alone and that contact is imminent or already occurring, there's psychological motivation to accept artificial explanations prematurely, to see every anomaly as confirmation, to interpret ambiguous data as supporting rather than questioning the hypothesis. This creates polarization, with two camps talking past each other, each accusing the other of bias, each convinced that their interpretation is objective, while the opposition is blinded by ideology. The scientific method is supposed to protect against both errors. You collect data without bias. You test hypotheses rigorously. You follow evidence regardless of whether it supports comfortable conclusions. But scientists are human. They're subject to the same psychological pressures as everyone else. And in cases where evidence is ambiguous, where multiple interpretations are possible, where the implications are enormous, maintaining genuine objectivity is extraordinarily difficult. Careers, reputations, worldviews, all of it is at stake, and that creates pressures that can subtly or not so subtly bias how data is interpreted. This is why the coordinated observation campaign for December 19th matters so much. With multiple independent teams using different techniques collecting different types of data, the probability of systematic bias affecting all results in the same direction decreases. If optical observers see an anomaly but spectroscopists don't, that's informative. If trajectory calculations show deviation, but photometry shows normal cometry activity, that tension needs resolution. The redundancy, the multiple perspectives, the diversity of techniques, all of it serves to average out individual biases and push toward consensus that reflects actual reality rather than collective preference. But consensus takes time. Even after December 19th, even with all the data collected during closest approach, there will be analysis to conduct, models to build, debates to resolve. The artificial hypothesis won't be proven or disproven overnight. It will be a gradual process of accumulating evidence, weighing alternatives, building confidence in one interpretation over others, and during that process, during the weeks and months of analysis and debate, the public narrative will evolve. Media will report preliminary findings, emphasizing whichever results seem most dramatic. Online communities will discuss and speculate, amplifying signals they find exciting while dismissing data that doesn't fit preferred narratives. Managing that process, ensuring that public understanding tracks reasonably well with actual scientific consensus, rather than diverging into speculation unconstrained by evidence, that's a challenge for science communication. Researchers need to share what they're finding without overstating certainty. Media needs to report accurately without sensationalizing, and the public needs to remain patient, accepting that complex questions don't yield simple, immediate answers, that science is a process of gradual refinement rather than sudden revelation. Avi Loeb has been a voice trying to model that approach, emphasizing curiosity and open-mindedness while maintaining scientific rigor. His public advocacy for taking the artificial hypothesis seriously has been controversial, drawing criticism from colleagues who think he's being reckless or attention-seeking. But Loeb's position is defensible. He's not claiming certainty. He's not insisting 3I Atlas is alien technology. He's arguing that the hypothesis deserves investigation proportional to its implications, that dismissing it without examination is unscientific, that we have an obligation to look carefully rather than assuming we already know the answer. And whether you agree with Loeb's assessment of specific anomalies, whether you find his arguments compelling or speculative, his broader methodological point stands. Science requires humility about uncertainty. It requires willingness to be wrong. It requires following evidence even when it leads to uncomfortable conclusions. Those principles apply to 3I Atlas, regardless of whether the object turns out to be natural or artificial. The lesson is about how we approach unknowns, how we handle ambiguity, how we maintain intellectual honesty when every instinct pushes toward premature closure. So as we enter these final days before closest approach, as observation campaigns activate and defense systems stand ready, and analysis teams prepare to process incoming data, remember that this is science in action. Messy, uncertain, evolving science where answers emerge gradually from accumulated observations rather than appearing fully formed. Whatever December 19th reveals, whatever the Jupiter encounter shows, whatever we learn from the debris field crossing in 2026, all of it will be provisional, subject to revision as new data arrives and better models are developed. An understanding deepens through the patient accumulation of knowledge that defines the scientific enterprise at its best, and which we're privileged to witness happening in real time with an object that, regardless of what it ultimately proves to be, has already taught us that the universe is stranger than our theories predicted, and that the most important questions are the ones we haven't figured out how to answer yet, but which we keep asking anyway because curiosity about what's possible exceeds our comfort with what's known. And that brings us to the fundamental question that underlies everything we've discussed, the question that December 19th and the Jupiter encounter and the debris field crossing are all designed to help answer. What is 3I Atlas? Not just in the descriptive sense, not just cataloguing its properties and behaviours, but in the deeper sense of what it represents, what category of phenomena it belongs to, whether it fits within our existing frameworks for understanding objects in space, or whether it's something fundamentally new that requires us to expand those frameworks or build entirely different ones. The natural hypothesis, the explanation that most astronomers favour by default because it requires the fewest extraordinary assumptions, is that 3I Atlas is a comet. An unusual comet, certainly, one with composition and behaviour that differ from typical solar system comets because it formed in a different stellar environment under different conditions. But ultimately just a comet, a frozen chunk of ice and rock and organic compounds that happened to get ejected from its birth system, that wandered through interstellar space for millions or billions of years, and that by chance passed through our solar system where we were fortunate enough to detect it. Under this framework, all the anomalies have natural explanations even if we haven't fully worked out the details yet. The trajectory precision toward Jupiter's hill radius is coincidence, 1 in a billion luck that happened to occur but doesn't indicate intentionality. The geometric emissions result from unusual but natural vent configurations, perhaps organised by fracture patterns in the nucleus that happen to produce symmetric jets. The antitail is a projection effect or rare outgassing geometry that looks anomalous but ultimately follows from known physics applied to unusual conditions. The X-ray detection indicates charge exchange working exactly as expected, but with composition variations that make it more efficient than in typical comets. This explanation has the advantage of not requiring anything new. We understand comets. We've studied them for centuries, sent spacecraft to visit them, analysed their composition and structure in detail. Extending that understanding to interstellar comets, allowing for some variation in properties based on different formation environments, that's conservative extrapolation from known science. It doesn't demand that we accept revolutionary new ideas about intelligence beyond Earth or technology from other civilizations. It keeps us in the familiar territory of natural processes producing diverse outcomes. But this explanation also has a problem. It requires invoking coincidence repeatedly. The trajectory just happened to target the hill radius with remarkable precision. The jets just happened to organize into geometric patterns. The anti-tail just happened to form in ways we haven't seen before. The composition just happened to produce X-rays when other interstellar objects didn't. Each individual coincidence might be unlikely but possible. But when you stack them together, when you require multiple independent unlikely events all happening in the same object, the cumulative probability becomes vanishingly small. At some point, invoking coincidence becomes less parsimonious than considering alternatives. The artificial hypothesis, the explanation that a growing number of researchers are taking seriously, even if they don't openly advocate for it, is that 3I Atlas contains technology. Not necessarily that the entire object is a spacecraft, not that it's obviously artificial like something out of science fiction, but that it's a hybrid object, a natural nucleus that has been modified or that contains embedded components serving technological purposes. This could be an interstellar probe that uses a cometary body as radiation shielding, as reaction mass for propulsion, as camouflage to appear natural. Or it could be a derelict, technology that's millions of years old, still functioning but no longer controlled, following programmed instructions that play out mechanically, without active intelligence guiding them. Under this framework, the anomalies make sense. The trajectory precision indicates active navigation, small course corrections executed by propulsion systems to achieve the desired approach geometry. The geometric emissions are thruster plumes, exhaust from directional propulsion arranged in symmetric configurations for balanced thrust. The anti-tail is exhaust from forward-facing thrusters, providing braking thrust, decelerating the object to enable orbital capture. The X-ray emission includes contributions from power systems or high-energy processes associated with active technology, rather than just natural charge exchange. Each anomaly isn't coincidence but evidence, indicators of artificial systems operating according to design. This explanation has the advantage of fitting the observations without requiring stacked coincidences, but it has the massive disadvantage of requiring something extraordinary, the existence of technology from another civilization, confirmation that we're not alone in the universe, and that intelligence capable of interstellar travel exists, and has sent probes that occasionally pass through our solar system. That's a revolutionary claim, one that would fundamentally change humanity's understanding of its place in the cosmos. And extraordinary claims require extraordinary evidence, a standard that many argue 3I Atlas hasn't yet met, regardless of how suggestive the anomalies might be. So we're left with a choice between an explanation that's conservative but requires implausible coincidences, and an explanation that's radical but fits the data more naturally. Neither is fully satisfying. Neither can be definitively proven with currently available information, and that's why the observations during closest approach and the Jupiter encounter matter so much. They're opportunities to collect data that might resolve the ambiguity, that might tip the scales decisively toward one interpretation or the other. What would constitute definitive evidence for the artificial hypothesis? Several signatures could do it. Direct detection of radio emissions that show modulation patterns inconsistent with natural processes would be compelling. Natural radio emission from space exists. Pulsars and magnetars and various plasma phenomena produce radio waves. But these emissions have characteristic signatures, random fluctuations or periodic pulses that reflect the physics producing them. Deliberate signals, communications or telemetry would show different patterns, structured modulation that carries information rather than just energy, or detection of trajectory changes that can't be explained by any plausible outgassing scenario. If 3I Atlas makes a sudden maneuver, a velocity change too large to attribute to jets, executed with timing that suggests deliberate decision rather than passive response to heating, that would be hard to explain naturally. Or if multiple smaller objects are observed separating from the main body, if companions deploy and maneuver independently, if we see clear evidence of a swarm rather than a single body, that would strongly suggest artificial origin. Or spectroscopic detection of molecules or compounds that don't occur naturally, that require industrial synthesis, or that have isotopic ratios too uniform to result from natural processes. Or radar returns showing geometric structures, flat surfaces at precise angles, shapes that indicate manufacturing rather than random accretion. Or thermal signatures indicating localized heat sources far hotter than solar heating can produce, temperatures consistent with nuclear reactions or plasma processes. Any of these would shift the burden of proof, would make the artificial hypothesis the explanation that requires fewer assumptions than the natural alternative. Conversely, what would constitute definitive evidence against the artificial hypothesis? Primarily, it would be comprehensive explanations for all the anomalies that don't require invoking technology. If detailed modelling can show that unusual but natural ice composition, produces exactly the observed geometric jet patterns. If charge, exchange with rare ionization states explains the X-ray spectrum completely. If sophisticated trajectory analysis demonstrates that the Hill radius approach is within the range of gravitational coincidences, even if unlikely, if every anomaly gets a satisfactory natural explanation, then Occam's razor favours the natural interpretation. You don't invoke extraterrestrial technology when natural processes suffice. The problem is that we're not there yet. Some anomalies have plausible natural explanations, others don't, or at least don't have explanations that have been worked out in detail and verified against data. The anti-tale remains deeply puzzling. The trajectory precision hasn't been adequately explained. The spectroscopic oddities could be composition variations but could also be something else. We're in the uncomfortable middle ground where neither hypothesis is proven, where evidence is suggestive but not conclusive, where reasonable people examining the same data reach different conclusions based on how they weight coincidence against radical claims, and that's the state we'll probably remain in even after December 19th, even after the Jupiter encounter. Science rarely provides sudden definitive answers to complex questions. It accumulates evidence gradually. It builds confidence in interpretations through repeated observations that consistently support one framework over others. The process takes time, requires patience, and often leaves uncertainty, even as understanding improves. So we should expect that 3i Atlas will remain controversial, will continue generating debate, will be interpreted differently by different researchers for years or even decades. But that uncertainty, that ongoing debate, is actually valuable. It keeps the question alive. It prevents premature closure. It ensures that if evidence does eventually emerge that decisively supports the artificial hypothesis, if we do get that smoking gun observation, there will be researchers who have been thinking about these questions, who have developed frameworks for analysis, who are ready to interpret the new data properly rather than dismissing it, because it doesn't fit conventional assumptions. The controversy around 3i Atlas, the willingness of some researchers to take the artificial hypothesis seriously despite skepticism from the majority, that creates intellectual space for discovery that wouldn't exist if everyone dismissed the possibility from the start. Now let's talk about what happens from a policy and communication perspective if the artificial hypothesis gains strong support. If observations during closest approach or the Jupiter encounter provide compelling evidence that 3i Atlas contains technology, how do governments and space agencies respond? This is where the defense drills we've seen become relevant, where the coordination between civilian and military space organizations matters, where decisions about disclosure and public communication become critical. The first question is who decides what gets disclosed and when. In the United States, that decision involves multiple stakeholders. NASA, as the civilian space agency, would have scientific data and institutional interest in transparency. The Department of Defense and intelligence agencies would have classified observations and institutional interest in maintaining operational security. The White House, through the National Security Council, would coordinate between these entities and make final policy decisions. And Congress would presumably want oversight, would demand briefings, would ask hard questions about why information was or wasn't shared with the public. Internationally, the situation is even more complex. If the United States has compelling evidence of artificial technology, do they share it immediately with allies, with potential adversaries? Through what channels? The UN Committee on the Peaceful Uses of Outer Space is the nominal international body for space coordination, but it moves slowly, requires consensus, and doesn't have enforcement mechanisms. More likely, initial sharing would happen through existing intelligence partnerships, Five Eyes nations first, then expanding to other allies, with public disclosure only after diplomatic groundwork has been laid. But there's a fundamental problem with trying to manage disclosure in a connected, surveilled world. Amateur astronomers are watching 3i Atlas. They're collecting their own data. If something dramatic happens, if the object does something obviously artificial, someone will notice independently of government observations, and they'll share what they see online, through social media, through astronomy forums and YouTube channels and everywhere else that information flows. Within hours, the story would be global even without official confirmation, and at that point, the choice isn't whether to disclose but how to respond to a disclosure that's already occurred organically. This is why some argue that proactive transparency is the better approach. Rather than waiting for events to force disclosure, rather than reacting to leaks or independent observations, Governments should share what they know early, providing context and analysis that helps the public understand what's being observed and what it might mean. That builds trust. It positions official sources as helpful and informative rather than secretive and potentially deceptive. And it allows for gradual adjustment to extraordinary news rather than sudden shock if something undeniable occurs. But the counter-argument is that premature disclosure, before evidence is conclusive, risks causing unnecessary panic or generating skepticism if the extraordinary claims are later walked back. If you announce that 3i Atlas might be artificial based on preliminary data, then subsequent analysis shows natural explanations are sufficient, you've damaged credibility and created confusion. Better to wait until certainty is high, until the evidence is strong enough that disclosure can be definitive rather than speculative. That's the conservative approach, the one that prioritizes avoiding false alarms over providing early information. Which approach is right depends on judgments about public resilience, about the likelihood of leaks, about the strength of current evidence, about strategic considerations that weigh transparency against control. And those judgments are being made right now by people whose names we don't know, in meetings we're not privy to, based on information we don't have full access to. That's frustrating for anyone who believes democratic societies should make important decisions democratically. But it's the reality of how national security and space policy intersect. What we can observe is behavior. The defense drills, the data-sharing protocols, the coordination between nations, all of this suggests preparation for scenarios that might require rapid response. Whether those scenarios involve confirmed artificial technology or just unusual natural phenomena that need careful tracking, we can't determine from outside. But the pattern of preparation is consistent with taking seriously the possibility that 3i Atlas represents something beyond routine astronomical observation. There's also the question of what contact protocols might be activated if artificial origin is confirmed. Do we attempt communication? Do we send signals toward the object trying to establish that we're aware of its presence and open to interaction? Or do we maintain silence, observing passively without revealing ourselves as intelligent observers? These questions have been debated in SETI circles for decades. The scenarios usually discussed involve receiving radio signals from distant civilizations, not encountering physical probes in our solar system, but the principles transfer. Some argue that if an advanced civilization sent a probe, they already know we're here. They can see our cities lit up at night. They can detect our radio and television broadcasts leaking into space. They can observe our satellites and spacecraft. There's no point pretending we're not intelligent. Better to acknowledge their presence, demonstrate that we're aware and curious, attempt communication on the possibility that they're interested in interacting. This is the proactive approach, treating contact as an opportunity for knowledge and connection. Others argue for caution. We don't know intentions, we don't know capabilities. Revealing ourselves more explicitly than our passive electromagnetic emissions already have could invite attention we're not prepared for. Better to observe quietly, learn what we can, build understanding of what we're dealing with before making ourselves more visible. This is the conservative approach, prioritizing risk mitigation over potential rewards of interaction. Both positions have merit. Both reflect different values and different assessments of risk versus opportunity, and there's no objective way to determine which is correct without knowing things we can't know, like what an observing intelligence's intentions actually are, or whether our actions make any difference to how they might respond. This uncertainty is paralyzing for decision-makers who want clear guidance, but it's unavoidable when dealing with scenarios that have literally never occurred before, where no precedent exists and every choice sets precedent that might shape humanity's cosmic future. Avi Loeb has been vocal about his belief that we should be proactive, that if 3i Atlas is artificial, we should attempt communication, that scientific curiosity should overcome caution. In his discussions, he's emphasized that the potential to learn from an advanced civilization far exceeds the hypothetical risks of making contact. If they wanted to harm us, they could have done so already, he's noted in various interviews. The fact that they're here observing rather than acting suggests benign, or at least neutral intentions. That's speculative but not unreasonable. An intelligence capable of interstellar travel presumably has capabilities that would make humans irrelevant as threats. If they chose observation over interference, that might reflect policy or ethics that value non-intervention. But critics point out that intentions could change based on our actions. A probe programmed to observe passively might have different protocols that activate if the observed civilization attempts contact or demonstrates certain capabilities, we're making assumptions about alien psychology or programming that might be completely wrong. The safest course, skeptics argue, is to gather information without revealing more about ourselves than necessary, at least until we understand better what we're dealing with. These debates will intensify if evidence supporting artificial origin becomes strong. They'll move from academic philosophy into practical policy, and the decisions made will reflect not just rational analysis but cultural values, institutional biases, political considerations, and the personalities of whoever happens to be in decision-making positions when the moment arrives. That's unsettling for anyone who wants humanity's first contact with extraterrestrial intelligence to be handled optimally. But it's realistic about how human institutions actually function, especially under pressure, especially when facing unprecedented situations. Now, regardless of whether 3I Atlas proves to be natural or artificial, regardless of what December 19th and the Jupiter encounter reveal, this object has already changed astronomy. It's demonstrated that interstellar visitors can exhibit behaviors outside the range of what solar system comets show us. It's validated the importance of studying these objects intensively while they are accessible, rather than treating them as minor curiosities. It's shown that anomaly detection in astronomy isn't just about statistical outliers, but about recognizing patterns that don't fit existing frameworks and being willing to investigate them seriously. The detection of X-rays from 3I Atlas, even if ultimately explained through conventional charge exchange with unusual efficiency, establishes that X-ray observation of comets and interstellar objects should be routine rather than exceptional. XRISM's success will likely lead to more frequent X-ray observations of cometary targets, building a database that can reveal whether 3I Atlas's X-ray emission is truly unique or just the first detected example of phenomena that occurs more broadly. That comparative context will be invaluable for interpretation. The anti-tail observations have already stimulated new modelling efforts, trying to understand under what conditions material can appear to flow sunward. Whether these models succeed in explaining 3I Atlas naturally or conclude that natural processes can't account for the observations, the scientific literature will be enriched by the detailed analysis required to address the question. That's how science advances, through challenging cases that push theoretical understanding beyond comfortable territory. The trajectory precision has reinvigorated interest in orbital dynamics of small bodies, in non-gravitational forces, in how subtle thrust can accumulate over long timescales to produce significant trajectory modifications. Researchers are developing more sophisticated models that can distinguish between chaotic outgassing and controlled propulsion, that can test whether observed trajectories are consistent with natural processes or require invoking directed thrust. These techniques will be applicable to future interstellar visitors, providing tools for rapid assessment of whether objects are behaving naturally or anomalously. And perhaps most importantly, 3I Atlas has normalized discussion of the artificial hypothesis in professional astronomy. Before Oumuamua, suggesting that any astronomical object might be artificial technology was career suicide, something that serious researchers simply didn't do. Oumuamua cracked that barrier slightly, making it acceptable to mention the possibility even if dismissing it quickly. 3I Atlas has pushed further, creating space for legitimate scientific discourse about how to detect artificial objects, what signatures would be definitive, how to design observations that test the hypothesis rather than just assuming it's false. That shift in scientific culture, the increased willingness to engage with ideas that were previously taboo, has value beyond just this one object. It makes astronomy more intellectually open, more willing to consider possibilities outside the conventional framework, more able to recognize truly revolutionary discoveries if they occur. And it connects astronomy to broader public interest in questions about cosmic context, about whether intelligence is rare or common in the universe, about what humanity's future might hold as we develop our own capabilities for exploration, and potentially encounter others doing the same. From an educational perspective, 3I Atlas is a gift. It provides a real-time case study in how science handles uncertainty, how evidence accumulates, how debates between competing hypotheses proceed, how observation and theory interact to build understanding. Students learning about the scientific method don't just get abstract principles, they get a concrete example unfolding in the present, where they can follow the observations, read the papers, see how researchers argue for different interpretations. That immediacy, that connection to events happening now rather than historical episodes, makes the learning more engaging and more memorable. And for the broader public, for anyone interested in space and astronomy and questions about life beyond Earth, 3i Atlas is a focal point for attention and curiosity. The story has reached mainstream media. It's been covered in major newspapers, discussed on television, analysed in podcasts and YouTube videos. Millions of people who might never otherwise think about comets or interstellar objects or planetary defense are now aware of these topics. They're learning vocabulary, orbital mechanics, spectroscopy, X-ray astronomy, all the technical concepts needed to understand what's being observed. That's science communication at scale, driven by genuine public interest in a mystery that hasn't been solved yet. So what should you, as someone who's made it this far through this analysis, take away from all of this? First, recognise that you're witnessing something genuinely historical. Whether 3i Atlas is natural or artificial, whether it's ultimately explained or remains mysterious, this object will be studied and discussed and referenced for generations. The fact that you're following the story as it develops, that you're engaged with the observations and the debates and the implications that makes you part of the process. You're not just a passive consumer of science, you're an active participant in collective human attention to a cosmic mystery. Second, maintain critical thinking about the information you encounter. There's a lot of speculation mixed with observation, a lot of interpretation mixed with data. Learn to distinguish between here's what we measured and here's what we think it means. The former is factual, verifiable, the basis for everything else. The latter is analysis, subject to revision, dependent on assumptions that might not be valid. Both are important, but they're different categories and should be evaluated differently. Third, resist the temptation toward premature certainty. It's comfortable to decide you know the answer, to commit to either the natural or artificial hypothesis and defend it against all challenges, but that comfort comes at the cost of intellectual honesty. The truth is we don't know yet. The evidence is suggestive but not conclusive. Maintaining uncertainty, staying open to being wrong, accepting that the answer might not be clear even after December 19th. That's the honest position and the one most likely to lead to truth eventually. Fourth, demand transparency from institutions. If space agencies have data that's relevant to understanding 3i Atlas, that data should be shared. If defense organizations have observations from classified assets, the question of when and how to declassify should be asked seriously. Science works best in the open. Democracy requires informed citizens. Both principles argue for maximum transparency consistent with legitimate security concerns, and those security concerns should be scrutinized rather than accepted uncritically as justification for secrecy. And fifth, maintain the curiosity that brought you to this topic in the first place. That sense of wonder, that desire to understand, that willingness to ask questions and seek answers, that's valuable not just for 3i Atlas but for life generally. We live in a universe far stranger than everyday experience suggests. Objects pass through our solar system carrying information about distant times and places. Technologies exist or might exist that exceed our capabilities by unimaginable margins. Intelligence might be common in the cosmos, or we might be alone for light years in every direction. These questions matter, they're worth thinking about. They enrich human experience beyond the mundane concerns of daily life. So stay engaged, watch for updates, read the papers when they're published, follow the observations during closest approach, pay attention to what happens at Jupiter. Check back in March 2026 when Earth passes through the debris field. Be part of the conversation, the global collective attention focused on this visitor from beyond. Because whether it proves to be natural or artificial, whether it's explained or remains mysterious, whether it changes everything or just adds another chapter to the catalogue of unusual comets, 3i Atlas matters. It matters scientifically, it matters culturally, it matters for what it reveals about how we handle uncertainty and mystery and the possibility of profound discovery. Before I close, I need you to do something. Drop your location and what time it is where you are in the comments below. Because as you finish reading this, as you think about X-ray detections and defense drills and the possibility that we might be days away from observations that change humanity's cosmic context, 3i Atlas is still moving. Right now, this second, it's travelling through space at velocities we can barely comprehend, approaching the moment of closest passage, carrying whatever secrets it holds toward their revelation. Someone in Tokyo is reading this at a different moment than someone in London, or New York, or Sydney. We're all scattered across this planet, separated by geography and time zones. But we're all looking at the same sky, wondering about the same object, asking whether this visitor means we're alone or accompanied in a universe we're only beginning to understand. Hit subscribe and turn on notifications because this story is not finished. When December 19th arrives, when observations from closest approach start coming in, when analysts begin processing the data and preliminary results emerge, you'll want to know. When the Jupiter encounter happens, when we see whether orbital insertion occurs or the object passes through, when the next phase of this mystery unfolds, you'll want to be informed. And when March 2026 comes, when Earth crosses through the debris field and we might intercept actual material from an interstellar visitor, when the next opportunity for discovery arrives, you'll want to understand what's being observed and what it might mean. We're living through a potential turning point. If 3I Atlas is confirmed as artificial, everything changes. Our place in the universe, our understanding of intelligence and technology, our sense of being alone or being observed, all of it shifts fundamentally. But even if it proves to be natural, even if every anomaly gets explained and we conclude this was just an unusual comet, we'll have learned that the universe produces phenomena we didn't anticipate, that our frameworks for understanding need expansion, that the next interstellar visitor might be the one that truly challenges everything we think we know. So stay curious, stay critical, stay engaged, demand answers when you can, accept uncertainty when you must, think for yourself, question narratives, follow evidence, and most importantly, keep watching. Because whether 3I Atlas represents first contact or natural phenomena, whether it's revolutionary or evolutionary, whether it changes everything or just adds complexity to what we already know, it's teaching us about the cosmos and about ourselves, and about how science works when confronting genuine mysteries that don't yield easily to familiar explanations, but which reward persistent inquiry with incremental understanding that gradually builds towards something approximating truth, even if we never achieve perfect certainty. The X-ray detection is real, the defense drills are happening, the global coordination is documented, the closest approach is days away. And whatever happens next, whatever December 19th reveals, we'll be here to analyze it, to discuss it, to figure out together what it means. That's the value of community, of shared attention to significant questions, of collective effort to understand rather than each of us struggling alone with complexity that exceeds individual capacity to process. We're in this together, watching together, learning together, preparing together for possibilities that range from mundane to world-changing, but which all deserve our attention because this is our solar system, our moment, our chance to see clearly what's passing through and to respond with the wisdom and curiosity and courage that the moment demands. So thank you for your attention. Thank you for engaging with this material. Thank you for thinking critically and asking questions and maintaining the intellectual honesty that science requires and that our situation demands. The story continues, the observations proceed, the analysis advances, and we'll be here, reporting what's known, acknowledging what isn't, following wherever the evidence leads because that's what this is about fundamentally. Not confirming favourite theories or defending comfortable assumptions, but discovering what's actually true about an object from another star that's passing through our cosmic neighbourhood right now. Carrying information we're only beginning to extract, representing possibilities we're only starting to explore, and demonstrating that the universe is exactly as strange as the data suggest it is, rather than as conventional as our theories would prefer it to be.